Well, muito obrigado. Não falo português, mas entendo um pouco de português brasileiro. But I'm going to speak in English because I'm going to be the same way we try to speak in Italian and we are just trying. So next time I promise I'll get a better more Portuguese.
Prego.
So well, this work is about generating text reports from medical imaging. I hope you enjoy this talk. It's a very interesting topic. And well, the slides I'm presenting are thanks to two students, Paulo Pino, who recently graduated, Paulo Messina, PhD student here at UC Chile, and also the speech and language processing book by Jurafsky and Martin. And I will share this slide later. You can see the website of the book. They are preparing the third version, and it's really good resource if you want to get into natural language processing. I also want to thank to Dr. Cecilia Besa from the School of Medicine at PUC Chile, Jocelyn Dunstan, Jose Cañete, an engineer at the Center of Artificial Intelligence, upcoming students who are starting their research in this area too, Francisco Madariaga, Ricardo Chilling, and Greg Chuit, and two undergraduate students who are working in this topic, Juan Pablo and Mario. So before I start with the topic of this talk, I want to spend a few slides telling you about the iHealth, the Institute on Intelligent Healthcare Engineering, where we do artificial intelligence and medical imaging mostly, and also about the CENIA. So here we are about 12 researchers in different areas, from physicians working in medical imaging, artificial intelligence, electrical engineers, and also people working in public policy. And the challenges that we are trying to address in 10 years of funding that we're going to get until 2031 are related to first creating fully quantitative medical imaging. Right now, there are many steps which are automated, but there are also many steps which are manual, and that make this process prone to errors and also a bit more less efficient than they could be. We also want to use a lot of the advances in artificial intelligence, especially in deep neural networks, but rather than relying only on data, we also want to use physics models. So we want to do intelligent physics informed medical imaging. We also want to leverage artificial intelligence, but in the form that it can be really used by people who are not maybe experts in this area, mostly doctors, but also people who want to consume the results of this, like patients. And that's why we have the stream 3 related to explainable AI and medical imaging for integrated analysis, diagnosis, and reporting. And finally, we are also aiming at using data which is being produced in a biobank in Chile. In this biobank, we are collecting data for more than 10 years of part of a population in Chile. So in the same way that the UK has the UK biobank, where they have a lot of information for many years of people that can help them produce better medicines, better treatments, we want to also have the phenotype, the characteristics of our population, so then we can aim at better vaccines, treatments, or drugs for treating different illnesses. That's about the iHealth. And about the National Center for Artificial Intelligence, the other research center where I belong. You see here the mascot, which is called Perceptrin, like a small perceptron. And we have also several PIs researchers, but the directors are Álvaro Soto from computer science in the Catholic University, and Marcela Peña, who is from development psychology and education, also from the Catholic University of Chile, but we have researchers from several other universities and associated researchers from different centers in Chile. Here we are developing 5 lines of research. One is that the most popular one for deep learning in vision and language. Another related to connecting the world of deep learning, but with a more logical and probabilistic approaches, neurosymbolic artificial intelligence. We are also interested in bringing the research and the results from neuroscience and from development psychology into generating new algorithms. And in this area, we have the BrainSpire AI. Just like in the eye health, we also have an area related to physics for machine learning. So we don't rely only on data, but also in equations and in knowledge that we might have already from different fields. And finally, we also have an area of human-centered AI where we want to address the issues like bias, discrimination, and other potential harms that can produce the use of artificial intelligence without a careful process. Okay, we also have actions in this area related to creating companies. We have, for instance, as our partners, Notco, a company who is also selling, I think, products in Brazil, like not milk, not ice cream, or not mayo, that they change the components of the food to make them based only on plants. So for many people who have allergies, for instance, to animal proteins, they don't have issues with this. Also the company CPD that we are showing here that started with basic research in robotics and now are producing robots in different supermarkets in Chile and in Colombia and in the United States. And we also have an initiative called OpenSenia, where many of the models that we are producing, not only in English, but in Spanish language models or vision models, we are providing them for free in platforms like in GitHub and also in Hugging Face. In this sense, we probably have a good potential of developing things with Brazil or with Portugal. So we can have models not only in English, but models that can deal also with our Latin-based language. Okay, with that said, I want to talk to you about the main task that we are addressing in our research, my own group here in Chile, which is this idea of using medical images and generating automatically reports, something that is in the realm of what is called now multimodal deep learning, right? We have seen for many years models that can classify, can detect objects, and can generate images, the same from the side of text and language, right? Can classify text, can generate text, but very recently we have seen how these two words were connected now, and given, for instance, an input text, you can produce an image, right? That is described by this text. And there are many interactions. So now we are able to build models that get different information, audio information, text information, video, image, into the same space. And then the task I'm going to describe here is related to how can we use this in medicine. So the first thing is the motivation for this work. I'm not sure that you have read all this, but probably some of them know this book called Deep Medicine by the physician, the Dr. Eric Topol, who indicates that in the US by 2016, there were 800 million medical scans a year. So they don't have enough radiologists that can analyze this and then finally write a report. And they are already automating many of these initial diagnostics, right? Because this is accounting for about 60 billion images. And this is even growing. This, as you see, was before the pandemic of COVID-19. So during COVID-19, many people were using X-rays and were using scans and MRIs in order to detect if they really had COVID, to then for prognostic, take them to the next stage in the process of care. So then medical imaging can become a very important factor in issues like the pandemic. And using artificial intelligence for medical image report generation can help hospitals to deal with this large and growing demand. And although some scientists, some of them very well known, like Hinton, one of the Turing Awards, the Turing Award, if some of you don't know, is like the Nobel Prize, but in computer science. And Hinton said a few years ago he got the Turing Award for creating deep learning. He said, well, if I was a physician, a doctor, I wouldn't even try to get into radiology, because all radiologists are going to be replaced in a few years. And in fact, that has not been the case. What we have seen is that radiologists are in need still, but they need to learn how to use tools of artificial intelligence in order to enrich their work. So when we think of radiologists checking images, we don't need to forget that the process is not that the radiologist goes directly to the patient, right? What we usually see is that the patient sees a primary doctor or a general doctor, and the doctor gets some initial indication, diagnostics, and then she or he requests an imaging exam. Then the exam can be of many kinds, right? X-ray, MRI, scanner, PET. And then the radiologists interpret these results, and then it gets back with the report to the primary doctor, who finally informs to the patient, right? And one example of this kind of reports is the one that you see here, where you see one or more images. In this case, we see an X-ray, frontal and lateral. We see some manual tags written by the radiologist, and there are the report is not just like plain text. It has some basic structure. Usually, first you have, in some cases, you are following the status of this patient. So you can see, well, we want to compare this image with the image that we took from this patient 2 weeks ago. Sometimes there are also indications like the age, maybe if the patient has chest pain or has some illness. And then we have the findings. Usually what we try to generate with this method of natural language generation is the finding section, which is describing the image, right? And then we finally have the impression, which is the conclusion that the physician, the radiologist, gets from all the information that she or he sees here. So, for instance, there are some research that what they do is that they take the findings and then they summarize and write the impression. That's like a automatic summarization tool, but maybe it doesn't even take into account the image, right? But what we want to do here is to take as input this image or images, and then we want to write the finding section, right? We have been working on this for already, I would say, 3 years. We wrote a survey of the different techniques and methods were published in 2021. We also published a few initial methods that were rather simple, but very effective compared to state-of-the-art methods. And we are working in a more recent version in the latest month. Now, if you want to see the whole components of this task, apart from the image and the patient background that the referring physician can provide, we have this model, and usually this model has this visual component that processes the image or the input images, then extracts visual features which are given to the language component, and then the language component is the one used to generate the free text report. But there are some additional things. For instance, we can provide some domain knowledge. If we have maybe an ontology, or maybe we have some physics model, we can also provide it to this full model here. We can also provide certain things that are going to be helpful for the physicians to interpret or to trust these results. For instance, a text heat map indicating the words that the model is paying attention to in the indication, or heat maps or some explainable methods that can tell you where the model is paying attention to in order to generate this report, or maybe some counterfactual image. For instance, it can tell you, well, this patient doesn't have cardiomegaly, like a big heart, because it's very different from this image. And it can provide you this kind of explanation too. And it can also, the model provide certain words, tags, or concepts that can help also the diagnostic function. So I describe here in general, I still haven't got into deep learning, but you have been probably hearing many talks, many palestras this week, and some of them have been related to artificial intelligence and particularly deep learning, right? And just quickly, for those who are still not very familiar with this, deep learning is a technique based on neural networks, where we have an input object, and we have a model that have layers and connections, and the goal of this model is to learn this connection, right? To learn the weights of this connection. And digamos, let's say, this fever for deep learning started in 2011, where we started seeing how these models were performing much better year by year, even at the point that in 2015, in some particular tasks, they were outperforming human performance, like in this case of object recognition in a particular data set. One of the important things, and I hope that by this time you have already got this idea of deep learning, is not only the fact that you can get very good performance, it's the fact that in the past, what we were doing in machine learning was getting input data, like images or text. We had to produce a representation of this, like how we represent text. Well, let's say a vector with words and weights. We had to do that manually in a way, and then use a traditional learning algorithm to learn and predict in a task. And deep learning is doing this very important change, where you have the input data, you have the deep learning algorithm, and the process is learning the features. You don't need to provide those features. This is the big change in deep learning compared to other machine learning techniques. And we have seen, of course, apart from the capacities of this model to predict and to make classification and to identify objects and things like this, also to generate things, and at very good quality, like GPT. We have been talking about ChatGPT for already a few months, and we are going to still talking about that for some time. We have seen also models that are able to generate different kinds of images, like GANs, which are very good at generating faces, or VQI, which are more controllable, or even models like DALL-E 2, where you can provide a text and then it can just generate the image by getting this text as input, right? Now, going back to our initial task, which is about from an image generating text, which is the opposite of DALL-E, where you provide text and you generate an image. I described that you have, let's say, an input image, and you use a language component that now we are going to call the visual encoder, right? And this visual encoder is usually a neural network, deep learning model. And there are families of these neural networks, like convolutional neural networks. Those are the CNNs. Famous models are like DenseNet, ResNet, etc., or the more recent image transformer models, like Visual Transformer 16, 32, etc. We got these visual features, and then that would be the language model. And here we have recurrent neural networks, like RNNs, like the ones that are showing here. But at least in this area, the transformers are in general the state of the art, much better than the previous recurrent neural network, right? And in this way, we would like to have this text that describes this initial image, right? So it looks very straightforward. And in this way, one could say, well, this shouldn't take much time to produce a system that we can just go and use in the clinic, right? We have this idea of encoder and producing a context, and then a decoder that writes the text. So then the encoder can receive, it's a very generic architecture. You can also provide text and then generate text. That's how a translation works. Or you can take pieces of images and generate pieces of images. It's a very flexible version, right? There are other applications, as I was saying, of this encoder-decoder network architecture, like machine translation, input one image, one text, output in a different language, or summarization, that as I was describing before. You can provide a long text, and then this model can write it in a shorter version, or question answering, what you have seen in ChatGPT. The fact that you are writing, hey, ChatGPT, give me, I don't know, this in Spanish, please translate it into Portuguese, and it can answer the question, and it can provide some generated text. Now, if we open a bit more these boxes, then we're going to see, for instance, this is one kind of visual encoder, a convolutional neural network, where we are going to have different filters, and these filters finally are summarized into a vector of global features. And then we provide this into a model that can be, in this case, a long short-term memory network, an LSTM, with the attention mechanism. Then you can be providing this text, right? And this would be the encoder, E, and the decoder, that usually the decoder is going to be a transformer rate, right? Okay. Now, one issue in the medical domain is that, unlike a general domain, like I don't know, training a model to classify cats or constructions or cars, when we are talking about medical information, we have like the privacy and sensitive data. So it's more difficult just to find these data sets. And in particular, the most popular data set in this area is called MIMIC, CXR, for X-ray, chest X-ray. And that's mostly the main, not that small data set in the area. There are not many more data sets. In the other areas of computer vision, you can find, apart from ImageNet, many other data sets right now for different tasks. But that's one issue that you need to solve, or you need to deal with. The fact that you don't have many different data sets, so it's more difficult to test generalizability. You want to make sure that your model is trained on one data set, to prove that it works well in a test data, but then you can test it on different, let's say, hospitals or different countries, but they don't have a public data of this. That makes it very difficult, right? So we analyze the different data sets, and as you see here in this table, maybe it's too small, but MIMIC is the only one that has a decent number, like more than 300,000 images and more than 200,000 reports. The other are way smaller, or they only have images, they don't have text. So maybe you can improve the training of the vision component, but then you don't have the language component in order to make the pairing in this multimodal version, right? And there is another data set which is rather good, which is the PATCHEST. It's actually in Spanish. It was produced in a Spanish hospital. The problem is that they filter the text, so it's not free text. It's like text after it has been filtered some words, stemming, cut the word, so it's not the same kind of information that you can get from MIMIC, right? And there are other data sets which are different parts of the body. That's the other thing, right? right now I'm going to be describing chest X-ray, which is the most popular. But what about training a model on chest and then trying to make a classification of an image and then write a report of brain? You cannot do it. You need, of course, different parts of the body. That makes it more difficult too, right? So we have 18 report data set and 9 classification data sets, and these are the main ones. This is also an interesting data set that Indiana University is open, but it's rather small. You have around 10,000 images and 4,000 reports. The biggest one and the most commonly used is this one, but again, it's from a particular population in the United States. So if you want to know if this works in Brazil, well, you don't know because you need Brazilian patients and data in order to test it and generalize it. Right? But then if you want to use this one, you have to go to this website called Physionet. You need required training too. You need to get into a website where you need to learn certain ethics management of patient data program. It's not that difficult, but it will take you about a full day in order to read the material, pass the test, and then after you show proficiency that you have finished and successfully completed this exam, then they will give you access to the data. One interesting thing, though, is that some people have been taking the data set and giving them richer information. For instance, there is this other data set also present in Physionet called the chest image genome data set. And what they did is that rather than just having text and image, if they found some anomaly, they in some of the images, 500 in particular, they produce the bounding box in the image. So if the image, the report says heart, they mention they draw the heart here, right? And then they also produce something like a network of concepts, right? Something like an ontology. So then you can connect illnesses with part of the bodies and with certain taxonomy, clinical taxonomy. So then you have richer image. Now with the 500 reports, they train a model and then they produce bounding boxes for all the rest of the images. Maybe they might have some issues, but it's good that you don't only have image and text, but you also have certain sentences that are mapped directly into the image, and this can give you a more precise data in order to train or fine-tune a model. Now, I was telling you that we have images, we are producing a report. How do we evaluate this? Because when we have, for instance, translation, we can tell, for instance, well, this text here in English is this text here in Portuguese, right? Now, how can we tell that this text report is describing correctly what is seen in this image? Well, it's not that simple because first you need to make sure that you are extracting the right diagnosis for the right organs, and in many cases the physicians they are not very structured in writing these reports. So really you need a way to first, only with the text data, you need to extract the features of diagnosis, right? And in particular, in this data set, in Mimic, that's not so difficult because they produce this. In a way, they produce a table where for particularly 13 images and anomalies, they tell you, this patient, for instance, has cardiomegaly, or has pleural effusion, or doesn't have this, okay? But they use an automatic tool to do that. And that automatic tool called the Chexpert Labeler is not perfect. It's analyzing the text with rules, and sometimes it tells you that the patient doesn't have this, and it actually has this. You need to check that. But if you believe in this Chexpert Labeler, which most of the time is correct, then you can check if your model is writing the text for these particular illnesses but only for checking these 13 particular illnesses. If you have something else that the model is able to detect and it's not written there, you are going to have a mismatch. And that's also an issue, the fact that physicians are not perfect. They also can make mistakes when they are providing the diagnosis for something. So we don't have a perfect ground truth or gold standard. But in terms of evaluation, there has been a proposal of several metrics in the area of machine translation. For instance, there has been quick progress in deep learning for computer vision and natural language processing, and this can potentially solve the task in very few years. However, recent research in this medical image report generation shows that the traditional metrics that you use in machine translation, like Bleu, Rouge, CIDR, might not measure what is needed for actual clinical use. And recent state-of-the-art methods that are based in very sophisticated deep learning architecture sometimes achieve disappointing results compared to naive baseline, and in terms of clinical correctness or factual accuracy. So let me give you an example. There is this metric using machine translation called Bleu that is counting engrams matches in the ground truth. It's precision-based. It has some penalties in terms of brevity, so it penalizes if you are giving a translation which is too small, and you have Bleu 1, 2, 3, or 4, depending on if you are using unigrams, bigrams, n-grams, etc. So here's an example. Let's say that you generated this translation from Portuguese to English. The fox jumped over the dog, and the ground truth is the fox then jumped over the puppy. So then you are not matching exactly this word here, but it means more or less the same, and you are missing this then, okay? So then you are matching words generated by words in the ground truth, and then you are seeing how good is the translation, right? You can do it with bigrams, I mean pairs of words also. And also there is this metric called Rouge, which is similar, but it's trying to find the largest common subsequence, right? So here you have a very large number of tokens, and here you're saying this is a very large subsequence because if I miss this in particular, then these are all matching here, right? Now, again, what I'm saying here is that when you are showing that method that produces a report, a clinical report, with a good Bleu and Rouge metric and performance, sometimes it doesn't mean that the diagnosis is really good. And that's a problem because we don't want only a report that we can read well, that it looks like a human wrote it. We also want the diagnostic, the clinical diagnostic, to be precise, right? And I was describing in the past this checks per labeler, and the checks per labeler, what it does is that takes the report, and then for these 13 abnormalities, it tells you, well, based on this text that you are saying, we are finding that cardiomegaly is positive, a large cardiomegaly positive, lung lesion is unmentioned. The doctor doesn't say anything, so we are going to assume it's negative. And then usually we calculate the metrics of matching the right diagnostic with these labels here, negative and positive. And in an example that I'm providing you here, there is a report that we want to see written by the model. And here is an example of a report that is written that have very good Bleu and Rouge performance, which are NLP metrics. But in terms of the checks per labeler, it's not finding the right diagnostic, because here it says heart size is mildly enlarged, and here it says heart size is normal. Now, you have two words that are matching, heart and size. So it's telling you, look, in terms of matching words, you are matching words. But the problem is that you are giving the wrong message, right? Then we have another example and another example. The second one doesn't have good metrics of Bleu and Rouge, but it has a better performance in terms of the diagnostic. And the last one doesn't have a match of almost any word. So it has very bad performance in terms of bleu and rouge, but it's giving the right diagnostic. So then, I don't know, what would you use for this tool? I would prefer to use the Shakespeare labeler, right? It's better if I have better bleu and rouge because I'm matching the right words. But if I'm not providing a good diagnostic, this is not going to be helpful in a clinical setting. And what this tells us also is that the state of the art on evaluating how well the report is written automatically in clinical terms is still in progress. So then we produce this initial work based only on a simple neural network that classifies different illnesses, and it has templates of phrases. And this simple method that we tested in 2 data sets. Finally, here I'm just showing a quick summary for the sake of time. We show that we have much better performance than many state-of-the-art methods in terms of Shakespeare and Mirki, which are metrics related to the diagnostic, but we have worse performance in terms of bleu and rouge, which is telling us that maybe our text, it doesn't look very natural, but we are matching the right performance, which is that we're showing here, right? So this is a problem that we have. Now the only issue with using templates is that if we are missing an illness, a diagnostic, we need to produce another template and another template manually. So it would be nice if we have an actual generator. And this is the last thing that we were working the last year. And here we are working in a conditional version that where we provide an input image, and we also input one hot topic vector where we are telling the method, we want you to write the report talking about the lungs, or talking about the heart, talking about the neck, whatever. And then by providing also this conditional version and a transformer decoder, we were able to obtain much better results than the state-of-the-art. And also, another very important thing that I didn't describe here is that we made sure that the model is looking at the image, because there was one paper we read where they described that these language generator models, in many cases, if you input any image, they are going to produce a text that looks nice, but it's not really taking into account the input image, which is the most important thing, right? So then you are providing like an average report and not a report related to the particular patient that you are observing there. So we're evaluating also that our report is actually taking into account the image that we are giving as an input. Okay, so there are also some state-of-the-art models based on transformers and in different techniques like reinforcement learning and natural language inference. But we also find that the validation in these works is not very strong, so there is more research needed. We also see that we need better works relating the output of the text with explanation on the image in terms of explainable AI. We're working also in this model I described at the beginning of multimodal learning. Like, I don't know if someone in the previous talk about CLIP, this model that is about learning a common space for these 2 modes, for images and text. And then in this space, you can use it to generate, but also maybe to improve the representation informed by the other modes. So which challenges are ahead? And we are very open to collaborate if any of you in the near future or in the far future want to work into this area, right? First, we need to expand to other pathologies. As I said, the Shakespeare labeler only tells you about these 13 pathologies. What about other pathologies? We need to create other labelers on the text and label images. We need to generate in other languages apart from English. As I said, Mimic is only in English. We want to generate in Portuguese, in Spanish, and in many other languages. We also want to deal with multimodal input data, the fact that we can input maybe one or more images and text information and videos or even tabular information about the patient in order to have a more precise report. We want to also add explanations. We need to work also in creating new data sets in order to test for out-of-sample distribution generalization with techniques like transfer learning and meta-learning. And we also need to improve the evaluation based on NLG, natural language generation metrics for this clinical task and for dealing with actual clinical diagnosis. And this is it. Thank you.
Okay, we have time for a couple of questions. Anyone? Okay, I'm going to start with a couple of questions here.
Professor, please.
Yes, I was wondering about the evaluation issues you mentioned. Two things, actually, starting from the second one, actually.
Yeah.
Do you look into readability isolated from correctness? Are there any evaluation metrics specifically to do that?
Well, supposedly the Blair Rouge Cider Meteor are metrics that somehow match tokens, n-grams, and they give you some sense of readability, right? The problem is that if I understood well your question, what we have found is that if you only evaluate that, you are not making sure that the clinical diagnostic is going to be correct. So you need to evaluate both readability and clinical diagnostic. And there are other metrics, but they have not been very successful in really giving us a state of the art, a strong state of the art.
Yeah, that's my point as well. I think correctness is the main target here, but maybe you can have a second metric just to show the readability aspect, thinking about the usability side of it for the physician in the end of the day. But in a sense, you're right, like the translation and summarization metrics do that to some extent, like Bleu and Rouge. I can steal more time with more questions, but I'll let you ask some if you have any. Okay. So before my question, you're being asked to stop sharing your screen so we can see you in full screen here.
Yeah.
That's much better. The other thing I was going to ask about
Brazil there.
Oh, right.
Very long ago. A map where there was Brazil already and there was no Chile. There was terra incognita.
It's a Brazil-centric vision of the planet. The other thing I was going to mention was about privacy. You mentioned that it's quite difficult to put together a task collection to evaluate tasks like this one. And I was reading recently about the new tracks that the Text Retrieval Conference is putting together this year. And they're facing a similar problem, but for different tasks, which is given that, let's say you're planning to run a clinical trial to test some new medicine, for example, some new treatment, and you need to find volunteers to serve as a cohort for your experiment. And they had trouble with privacy issues because the task would be given the description of an intended clinical trial, find me electronic health records for matching patients, but then again they had trouble finding or having access to these electronic medical records. So what they did, which is perhaps applicable to the scenario you just described here, was to flip the problem. So essentially, they put together a synthetic patient record constructed by trained physicians. And the task was given that synthetic electronic medical record systems, participant systems should find matching clinical trials where that synthetic patient could serve. I was thinking whether flipping your problem makes sense to produce some task collection, like instead of giving an image, produce some report. Maybe clinicians could more easily put together a report, and I don't know if there's any publicly available database of images you could use to, I don't know, serve images that match that report, and then maybe this is going to be easier for people for judges to tell whether the image matches the report instead of whether the tax report matches the image. I don't know if it makes sense.
Yeah, we have been thinking of different options in this sense. The one that you said, we mentioned it, but we haven't progressed in that area in particular. But it looks actually very interesting because one problem with these reports that doesn't make it very straightforward to use the usual methods, like the one I described before, DALI, right? You provide a short text and then you generate an image. The problem is that the text report describing an X-ray sometimes can be very long. Even the methods like clip receives as an input like BERT, like 512 tokens, right? So what most people do is that they sample the report and then they provide the image and they try to learn a common embedding. But that's not usually the case. Maybe you are missing the most important part of the diagnostic because you are sampling part of the text, right? So the idea of using the task the other way around, like providing a text and then providing several images and telling the doctor which of the image really matches this text that we are seeing here, that can be very interesting in order to collect data. I'm not sure how that can help with privacy particularly, but other thing that I have heard related to dealing with privacy is this area of federated learning, right? Where you can maybe go and move your algorithm to different locations or servers, train there, get the gradients, and then put them together in order to train a full model. And another thing that is becoming also like a potential idea to deal with this is, you mentioned doctors generating a synthetic report. But how doctors generate a synthetic image? Well, you can use the new methods for generating like Midjourney that you can describe maybe something. The problem is that in the case of clinical information, you need to make sure that that is really, really realistic, because maybe you are producing an image that has an artifact, and then another method that is used to train this model based on these synthetic images can use these artifacts and be biased. But just today, I learned of a challenge that was opened by Association of Physicians in the US related to creating models that generate medical images and making sure these images comply with certain biomarkers and characteristics that we can say this is an actual, this doesn't only look like a medical image. It has the characteristic that we usually measure that makes you think this is synthetic, it's private, it's not of a patient, but it's realistic, really realistic, right? So there are many ideas in this realm. Ones are the ones that you described, and it's very exciting actually what is going to happen because of these issues, particular issues in the clinical domain with generative models and language models and deep learning for vision.
Right, great. Any quick last-minute question? Okay, so let's thank the speaker again. Thanks a lot for joining us, Denis.
Thank you. Muito obrigado.
Obrigado.